An array like the Atacama Large Millimeter Array covers kilometers of desert, yet it does not function like a massive version of a traditional camera. The high-resolution views published by these observatories are the result of capturing a sparsely sampled set of baseline correlations between the dishes. These correlations, known as visibilities, map information into the spatial frequency domain, a coordinate system astronomers call the UV plane. This raw data is inherently incomplete, further distorted by the Earth's atmosphere and the telescope's own receiver electronics before it is ever recorded. Reaching a clear image from these corrupted, partial samples requires a computational process that accounts for every physical interference encountered by the signal. The Common Astronomy Software Applications package, or CASA, serves as the primary engine for this work, processing data for ALMA, the VLA, and ASCAP. To manage the extreme volume of radio data, CASA separates high-level user logic from the low-level numerical libraries that perform the heavy computing. It operates through a specific sequence. It organizes samples into relational structures, applies algebraic calibration, and uses iterative Fourier deconvolution to build the final model. This architecture provides the framework necessary to translate raw receiver voltages into a recognizable view of the universe. The ingestion process begins with the raw correlator output, recording the exact time, the specific baseline, the observed frequency, and the polarization. CASA organizes this multidimensional data using the CASA Core Table Data System, storing observations in a relational format called the measurement set. At the center is the main table, containing the bulk complex visibility matrix, the data column, and the array's spatial coordinates, the UVW column. Because repeating metadata for every single integration would lead to unsustainable storage requirements, the measurement set employs database normalization. The main table uses integer IDs to link to peripheral subtables, like antenna, where telescope details are stored once and referenced. During processing, CASA generates new bulk columns for corrected visibilities and the sky model, preserving the raw inputs in their own column. This normalized architecture allows the system to iterate through the complex calibration steps without redundant data bloat. Calibration moves beyond storage, acting as a bootstrapping process to determine exactly how the signal was altered between the source and the detector. This is defined by the measurement equation. The observed visibility, Vij, equals the true visibility, Vtrue, multiplied by a baseline error operator, J. In CASA, the baseline operator is factored into the tensor product of two antenna-based Jones matrices. This factorization changes the mathematical scale of the problem. It reduces the number of unknowns from the square of the antennas, the baselines, to just the number of antennas themselves. The Jones matrix represents a physical sequence. The F matrix models the ionospheric effects encountered first, such as Faraday rotation and dispersive delay. Below that, the T matrix accounts for tropospheric path length variations and opacity, often resolved using data from water vapor radiometers. Finally, the B matrix models the bandpass response, the amplitude and phase variations introduced by the telescope's own electronic filters. CASA tasks like GainCal and bandpass solve for these matrices by comparing observations of the science target against known, stable calibrator sources. Applying the inverse of these aggregate matrices to the raw data column produces the corrected data needed for imaging. Finding the true sky brightness, I, requires solving the relationship between the corrected visibilities and a measurement operator, A. The operator A combines a two-dimensional Fourier transform with the specific spatial frequency sampling of the telescope array. On the left, the true sky brightness. In the middle, the point spread function. Because the physical array has gaps, this measurement operator isn't simply invertible. Convolving the sky with this point spread function produces a dirty image on the right, dominated by interference patterns. To recover the source, CASA uses nonlinear deconvolution algorithms, such as multiscale clean. The clean process iteratively identifies peak emissions, subtracts the point spread function, and builds a representation of the source from the remaining signal. The final output is a statistical model of the sky, reconstructed from the information sampled by the interferometer. Developing a software framework capable of these operations was a decades-long engineering challenge. An earlier attempt in the 1990s, AIPS++, tried to build the entire system in object-oriented C++, but the project struggled with its own internal complexity. A 1992 memo from the project's planning phase noted that the system's design had separated operations from data so thoroughly that it had become unusable for working astronomers. In 2004, the effort was reorganized into CASA, moving away from a monolithic structure and toward a modular design. The modern architecture places the rigorous C++ math libraries in an independent package called CASA Core, wrapped in Python-based interfaces. This modularity allows observatories to run automated pipelines through Python scripts, utilizing the efficiency of compiled C++ for heavy linear algebra. By aligning its data schema with the physics of radio interference, CASA provides tools to see what the atmosphere and electronics otherwise hide.